Some tourists in the Museum of Natural History are marveling at some dinosaur bones. One of them asks the guard, "Can you tell me how old the dinosaur bones are?" The guard replies, "They are 65,011,000 years old." "That's an awfully exact number," says the tourist. "How do you know their age so precisely?" The guard answers, "Well, the dinosaur bones were 65 million years old when I started working here, and that was 11 years ago." Now, that's an old joke that's been around for a while, but it's funny. And the reason it's funny is because we use numbers in different ways. The guard was using numbers mathematically, thinking that 65 million years plus 11 years is equal to 65,011,000. And that's correct. If the age of the dinosaur bones when he joined the museum was exactly 65 million years, then that would be totally correct. But we know that 65 million years is approximate. Those bones were about 65 million years old. And so 11 years later, they're still about 65 million years old. Here's another example. I found this cardboard box on a website online, and according to the manufacturer, the cardboard box has dimensions of 14 inches by 12 inches by 8 inches. And so we want to know, what's the volume of this box in cubic inches? So you all know how to find the volume of a box. It's the length times the width times the height. And if we take these numbers and multiply them together, we get 1,344 cubic inches. But hang on a minute. Is this box exactly 14 inches long? Or is it maybe between 13.5 and 14.5 inches, so that after you round off, it rounds to 14 inches? Or maybe it's a little bit more precise than that. Maybe it's between 13.9 and 14.1 inches long. And we can wonder the same thing about the other dimensions as well. So it seems reasonable that these dimensions may be accurate to within 1/10 of an inch. And so if we think about the ranges of the values for the length, the width, and the height, the length could reasonably be anywhere between 13.9 inches and 14.1 inches. The width could be anywhere between 11.9 and 12.1. The height could be anywhere between 7.9 and 8.1 inches. And if you look at the ranges of values that you get by multiplying these out, the answer could be anywhere between 1,306.739 cubic inches and 1,381.941 cubic inches. And if you look at this range of possible volumes, you can see that the 1 and the 3 those digits are certain. We're sure that the answer starts with a 1 and then it has a 3, but everything after that could really be just about anything. And so, really the best we can say is that the volume of the box is 13 something something cubic inches. So we need to deal with uncertain values all the time. And this is especially true in sciences like chemistry. And so we need to understand how to deal with numerical uncertainty and how to show numerical uncertainty. If we want to communicate a number to someone else, how can we show how much uncertainty there is in that number? I'm going to use another example of a company that sells ball bearings, and these ball bearings are manufactured to be between 3.1739 and 3.1765 centimeters in diameter. So the ball bearings are manufactured to be a certain size, but there's a little bit of variation, and the range of values is between 3.1739 and 3.1765. If you look at the range of values here, the 3.17 are that's fixed, that's certain, but the next two decimal places those are uncertain. It could be anywhere between 3.9 and 6.5. So the actual diameter of one of these ball bearings is in a range. There's some range of possible values that it might have, and this range is centered on 3.1752 centimeters. That's the midway point between the two values that were given. But the number could be lower than that by 0.0013, or it could be higher than that by up to 0.0013. All we can really say is that it's somewhere in that range, or at least it's probably in that range. I suppose there might be some freak accident where it's outside the range, but it's probably in that range. And if we wanted to communicate that, one way that there are a variety of accepted ways of representing this number to show the uncertainty in its value. One of these is the so-called standard error notation, where we would say that the diameter is the middle of the range, 3.1752, plus or minus 0.0013 centimeters. And this conveys the idea that the diameter is probably close to 3.1752. And how close is it to that value? Well, it's probably within 0.0013 centimeters. So this is one way that we could represent the uncertainty in this value. Another way that we could sort of express the same idea in more concise notation would be to write this as 3.1752 and in parentheses 13 centimeters. And in this notation, it's understood that those digits in parentheses represent the possible variation up or down in the last digits of the number. So these are some ways that people use to represent uncertain numbers. Another way that people do this, and this is the method that we're going to be using, is significant figures. And in using significant figure notation, we would just represent this number as 3.175 centimeters, where the first three digits are certain. We know that the value starts with 3.17, but we don't know for certain what the digits are that come after that, and we write down the first uncertain digit. And so we know that the value is close to 3.175, but that 5 could be a little bit lower or it could be a little bit higher, and certainly any digits after that 5 could be anything. And so these are all different ways to represent error, and all of them have their fans, but significant figures are probably the most common way for people with scientific training to represent the uncertainty of a numeric value. So coming back to the examples that we started with, the age of the dinosaur bones, well, if it is 65 million and something years old, we could express that in scientific notation, in using significant figures, as 6.5 times 10 to the 7 years. And so this conveys the idea that we're certain about the 6. The 5, we're not completely certain about. It could be 6.4 something, it could be 6.5 something, but it's close. We think it's close to 6.5 times 10 to the 7 years. So this would be a way of expressing the uncertainty in the age of that dinosaur skeleton. And in the case of the cardboard box, where we had calculated a volume of 1,344, but we weren't sure about those two 4s, if we wanted to express this number using significant figures, we could write it as 1.34 times 10 to the 3rd cubic inches, where the 1 and the 3 are certain, but that 4 is not. It could be a little bit lower than that, it could be a little bit higher than that. And so this significant figure notation, like I said, is widely used across the sciences, and And so it's important to understand how it's used and how to interpret it. Now, where we're going to be encountering significant figures is involves measurements. So anytime you measure something, there's always some uncertainty in the measured value. And so let's say that we wanted to measure the width of this hexagonal nut here. One way that we could do that is we could bring up a ruler and we could look at this, and looking at the markings on the ruler, we can see that the width of the nut is a little bit more than 1.7 centimeters and a little bit less than 1.8 centimeters. And so if we wanted to record the width of the nut, we're sure that it's between 1.7 and 1.8. We don't know exactly what it is between those values, but we can estimate. We can look at that by eye and say, okay, well, it looks like about 1.74 centimeters. Now, somebody else might look at it and say, no, that looks to me like 1.73. Someone else might say, well, to me that looks like 1.75. But the point is, we're sure that it's 1.7 something. The 4 here is uncertain. We think it's probably close to 4. It might not be exact, but that's our best guess, and so that's how we would write down the number as 1.74, with the understanding that that 4 is an uncertain digit. Now, if we had better apparatus, we could determine the size of the nut to more decimal places to greater precision. So if we had micrometer calipers, for instance, we might be able to determine that the width of the nut is 1.746 centimeters. So you can use fancier measuring devices to get more precise answers. But the downside is these fancier devices are going to be more expensive and they're harder to use. And so having extra digits of precision, it's desirable, but it's also expensive. And so there's always a trade-off between the precision of a measurement and the cost and the ease of making that measurement. Another way of looking at that is that if you have a number, the significant digits in that number are valuable, and you don't want to waste them. And I'll explain more about that in just a minute. So a lot of things that you would measure by eye are going to work the same way as using a ruler. So a lot of measured quantities, the apparatus that we use to make the measurement is designed so that we're visually comparing something against a series of markings. So for instance, if you wanted to read the volume of a liquid in a graduated cylinder, you'd be estimating the position of the height of the liquid against markings on the scale. If you wanted to weigh something using a triple beam balance, this involves visually comparing a slider against markings on a scale. If you wanted to use an analog thermometer, this involves visually comparing the length of a column of liquid against markings on a scale. And for all of these measurements, you would be able to read off certain digits based on the markings, and then you would be able to estimate one extra decimal place. That would be an uncertain digit. And so whenever you're reading off a numerical value using any kind of apparatus like this, you're always going to be estimating one extra decimal place beyond the markings. And this is true even for electronic devices. So something like this scale here, which is being used to weigh a beaker of liquid, it displays a mass of 95.85 grams. And if you didn't think about this very much, you might interpret that as meaning that the mass is 95.8500000 grams, but it isn't. If you look at the way that a balance like this works, it has all kinds of electronic circuitry, and the mass on the balance is turned into a voltage. That voltage is constantly fluctuating. It goes through the circuitry, it's processed into a number, but the last digit in that display is an uncertain digit. If you were to take that beaker of liquid off the scale and then put it back on, it might come up as 95.84 grams or 95.86. And that's the way these devices are designed. They're designed so that the last digit on the display is uncertain. But all of the digits that are displayed are considered significant. So you've got a bunch of certain digits and then one uncertain digit.